Greetings. This is a transcription of the notes of the lecture that was delivered in the classroom on February the 9th. We want to begin thinking about the curvature tensor. To start with, we will have a vector field. A vector field is simply a procedure that acts like this. Give me a point of the space that I'm in, and for each point, there's a vector associated with it. At point S of the space, there's a vector v of s. Now, this vector is whatever it is. A vector field accepts a point of the space and gives a corresponding vector back again. So I could imagine just starting off at point S and looking at what the vector that goes with it is. I could also do other things. As in my picture here, I could start at point P, travel to point Q, and then travel to point S along some pathway or the other. Every point on that pathway is going to have a vector to go with it, but regardless of what happens along the path, when I end up at S and look at the vector that goes with my destination point, I have to get the vector v of s. Of course, on the other hand, I could have started off at point P, traveled to some other point R, and from R traveled to S, encountering a wide variety of vectors along the path. But again, at the end, when I've arrived at my destination, I take my destination point S, evaluate my vector field there, and I must have V evaluated at S there as well. I must have the same thing that happened along the first path. To make this a bit more quantitative, I'm going to suppose that the coordinates of my starting point P are x1 through x3 or x0 through x3 or whatever dimension space I'm in. The coordinates of point Q are one coordinate at a time larger than those of P by an E number. The coordinates of point S are going to be larger than those of Q by D numbers. And to round out my roughly parallelogram looking thing, I'll also have a point R. Point R has coordinates that are equal to those at point P plus the D numbers. What I'm going to do is I'm going to analyze what happens to vector values as I travel along this first pathway. I'm going to express the final result as v at s along path 1. And what I really want to do is I want to express that value, or at least maybe the components of that vector, in terms of quantities that are evaluated at the original starting point P. So I'm going to start with the coordinates at P. I'm going to add the E numbers to those to end at Q, and then add in the D numbers to end at S. To start with, I'm going to express V alpha along path 1 at S in terms of the quantities at Q. V at S is V at Q plus the rate at which V changes times how much I changed the inputs. So I will write V alpha along path 1 at S is V1 component alpha at Q plus the rate at which the components of V are actually changing at Q times how much the inputs change. When I write covariant derivative, I'm taking into account dependence of both components and basis vectors. Now, I need to do two things. Firstly, I need to write this quantity in terms of p numbers. I also need to write this quantity in terms of p numbers. The first part is not too difficult. V alpha along path 1 at Q is V alpha at the original starting point P plus the rate of change of V alpha at P times how much I changed the input when I went from point P to point Q. These will be the E numbers. The first part is fairly direct to write out. Secondly, I need to know V alpha semicolon beta along path 1 at point P in terms of V alpha semicolon beta at P. This is where things are going to get a little tricky. The quantity of interest at Q is the quantity of interest at P plus the rate of change of the quantity of interest at P times how much the input changed as we went from point P to point Q. The quantity that I'm interested in is a value of the covariant derivative of V with respect to beta. That generally is a function of all the coordinates. I could find rates of changes of that quantity by doing covariant derivatives of it. Covariant derivative with respect to x gamma. Then, because of the chain rule, I have to multiply by e gamma and then sum up over the lowercase gamma. So, writing all of these quantities in, V alpha at S obtained by traveling along path 1 is given by this expression. When I don't say evaluated at some place, it's given to understand I'm evaluating all of these quantities at the original starting point, P. So multiplying all of this stuff out, I get this fairly horrific looking formula. One comment that I want to make before I go on to path 2 is this. In this expression that I'm looking at, beta and gamma are indexes of summation. I could rename those indexes by other letters if I felt like it, which, as it turns out, I'm going to. If I want to go along path 2, I start at P, then I go to R, then I go to S. If you think about what you're just doing the E numbers first and the D numbers second, as opposed to doing the D numbers first and the E numbers second. So instead of sitting down and writing out a bunch of formulas, I'm going to take my previous formula. Every place where I see E, I'll write D down and vice versa. The gamma and the beta are still indexes of summation, so if I feel like using other labels, I could do that as well. In my second path, I'll look at the equation for the first path. I'll interchange the E and the D, and it'll prove convenient for me to interchange indexes gamma and beta. That is, every place where you see a beta in the original, write gamma instead, and write every place where you see a gamma in the original, beta instead. So you can simply write the result down. If you'll observe, there's a lot of commonality going on here. V alpha, V alpha. Here I have V alpha comma gamma E gamma, V alpha comma gamma E gamma. Here I have V alpha semicolon beta D beta. Here I have V alpha semicolon beta D beta. Here I have an E gamma and a D beta, E gamma, D beta, but now I have to be careful. I have a second order covariant derivative. If these were ordinary partial derivatives, then they would commute and those two terms would be the same. We have no idea if that's the case for the second order covariant derivatives, so we're going to have to be careful. Since these two things are supposed to be the same in any sense, in the situation that we find ourselves, if I subtract one from the other, I have to get zero for an answer. The way I've got it written it here, I'm going to look at V1 minus V2. As it'll turn out, most textbooks would order it as V2 minus V1. It's just a matter of convenience. If one of those two things is zero, the other one is also. But when I subtract these two quantities, lots of stuff cancels out, and all that's left is a V alpha semicolon beta semicolon gamma E gamma D beta minus V alpha semicolon gamma semicolon beta D beta E gamma. And thanks to the fact that I interchanged indexes beta and the gamma on that second one, I can factor the E gamma D beta out. This difference, which since we're in a flat space, even though we're using some arbitrary coordinate system, this difference is zero. That means that these quantities all have to be zero in the case where we're using arbitrary coordinates in a flat space. Since this has to be true regardless of the exact values of the E numbers and the D numbers, my condition that things are the way I think they are is that this should be zero. This seems to say that I'm being unnecessarily concerned about whether or not these covariant derivatives are commutative in the beta and the gamma, because since the spaces are always perfectly flat, and perfectly flat means the same as this, then this certainly must always be true. Another thought is, if you give me a vector and I form its first covariant derivative, the numbers that I get, the V alpha semicolon beta, for instance, are the components of a 1-1 tensor. When I do the next covariant derivative, I get V alpha semicolon beta semicolon gamma, which are the components of a 1-2 tensor. I could think of this, and likewise that, as being components of two different 1-2 tensors being subtracted. A good question to think about is, what does it mean for this to actually always be zero? What's the formula going to be? It could be the case that this difference that I'm wanting to look at is the result of feeding a vector v and parenthetically e and d into some 1-3 tensor. If that's true, what is that tensor? We will look at V alpha semicolon beta semicolon gamma in some detail. Once we have that in our hands, we will get V alpha semicolon gamma semicolon beta almost for free by simply interchanging the indexes beta and gamma in the first formula. Firstly, I'll look at V alpha semicolon beta semicolon gamma. That's the semicolon gamma of V alpha semicolon beta. We have previously stated that V alpha semicolon beta, though, is the alpha beta component of some 1, 1 tensor. This tensor has components that have two different indices. One of them is a vector-like index. The other is a one-form-like index. So to do the covariant derivative with respect to x gamma, we follow our recipe and obtain this. So doing product rules and so forth, we get this result. V alpha semicolon beta semicolon gamma is V alpha beta comma gamma plus gamma alpha kappa gamma V kappa beta minus gamma mu beta gamma V alpha mu. To get the corresponding equation for V alpha semicolon gamma semicolon beta, as we said, we just interchange the indexes. I can save myself a good deal of writing if I notice something. This term has V components, V alpha mu, and this one has V alpha mu. This coefficient is Christoffel mu upstairs, beta gamma downstairs. This one was obtained by interchanging the beta and the gamma, but if you remember, the Christoffel symbols are symmetric on the two lower indices. So in that first formula and in the second formula, the trailing terms are equal to each other. When I subtract these two things, which is what I'm going to do, the last terms will cancel out. So even at this stage, I may as well forget about them. So we will just look at that first one, and then later we'll subtract away the same thing, except with the beta and the gamma interchanged. I need to look at V alpha beta comma gamma plus Christoffel alpha kappa gamma V kappa beta. Now, V alpha beta is also known as V alpha semicolon beta. It's the alpha beta component of the 1, 1 tensor obtained by doing covariant derivatives on vector V. Likewise, V kappa beta is V kappa semicolon beta. We have formulas for how to write out derivatives, covariant derivatives of various quantities. So writing down the recipe, we find out that the quantity we need to look at for V alpha semicolon beta semicolon gamma is the comma gamma partial derivative with respect to x gamma of the quantity that we wrote down using our recipe plus gamma alpha kappa gamma times the covariant derivative component that we get by following our recipe. So if you write out all of this stuff, it looks pretty awful, but you can at least get an expression. It's important to remember comma means ordinary partial derivative. After a rather large amount of calculating, it turns out that V alpha beta, V alpha semicolon beta semicolon gamma is equal to this tremendously ugly looking expression. If you interchange indexes beta and gamma, you'll get V alpha semicolon gamma semicolon beta. What I've done on this line is I've just written the previous line down again, except every place where I see beta, I say gamma. Every place I see gamma, I say beta instead. Since we're going to subtract these two things, we should go off and look for things that might cancel out. This is the ordinary second derivative of V alpha, first with respect to x beta, then with respect to x gamma. This is the ordinary second partial derivative of V alpha, first with respect to x gamma, then with respect to x beta. Because of the way second partial derivatives act in third semester calculus, these two quantities are the same. When I subtract, the things with a single underline beneath them are going to cancel out. Here, I have a Christoffel symbol times a V something comma something else symbol. There's an alpha, which is an actual index. There's a beta, a gamma. Those are all actual indexes. And the mu is an index of summation. Meanwhile, down in the other one, I have a gamma with an alpha upstairs. I have comma lowercase gamma. I have beta as the second index on the Christoffel symbol, and the kappa is an index of summation. This term and that term are the same. So when I subtract, they cancel each other out. And lastly, I have a Christoffel. I have a partial derivative of a component of a vector. I have alpha upstairs, gamma in the second index on the Christoffel, beta as the partial derivative index, and kappa is an index of summation. Here I have alpha upstairs on the Christoffel, gamma in the second position index, beta is the variable with which I am differentiating with respect to, and mu is an index of summation. So this quantity and that quantity are the same. When I do the subtraction, those will cancel out also. So the only thing that's going to remain is one, two terms here, and then another term and another one to be subtracted away. When the dust finally settles, I'm going to have four terms. If you'll write all of that out, you'll notice that because I've been careful about how I write my indexes down, the index on the V component is mu for all remaining terms that didn't cancel out. So I can pull the V mu out, and I'll find out that this quantity, which in the flat space case, possibly curved coordinates, this quantity that must be zero is this enormously messy looking thing times V mu. There's an index mu downstairs on every term inside the bracket. So this says this difference is this quantity in the bracket that doesn't depend on the vector v times components of v and then add up. We'll make an abbreviation. We're going to call the quantity inside the brackets R alpha mu gamma beta. I'm now adopting the same kind of ordering that most textbooks use. R alpha mu gamma beta is this derivative of a Christoffel symbol minus that derivative of a Christoffel symbol plus this product of two Christoffels minus that product of two Christoffels. It is possible to prove that the R, alpha, mu, gamma, betas actually are the components of a 1-3 tensor, but I'm going to avoid talking about that in this video. But what if this happened? You started at point P, you went to point Q, you ended up at point S, and having landed at S, V evaluated at S looks like this. You start at point P, you go to point R, and then to S. Having arrived at S, you calculate V of S, and it looks like that. If we are in the situation that we said we were in, that is impossible. That can't happen. What was that situation? We're in a flat space, even though we might be using curved coordinates. If that's true, I have to get the same V of S at the end. So if flat space, then this can't happen. Take the logical contrapositive of that. If this bizarre thing happens, then I am not in a flat space. For example, I could imagine being on the surface of a sphere that is so large that when I look around, it looks flat to me. If I fooled myself into thinking like a flat earther, I could start at some point on the equator with some little arrow, and I would travel with my little arrow along the surface, never letting it change direction, at least as far as I can see on my little local flat patch of land. And when I get to the eastmost point, my vector is going to be pointing into the plane of the paper. Or I could have taken that same vector and done the same thing traveling to the North Pole, and then from the North Pole travel to this easternmost point on the sphere. My vector will be in the plane of the paper then, pointing downwards. So all of the R, alpha, beta, gamma, delta numbers, they have to be zero at all points if I'm to have a flat space. If even one of those numbers is different from zero any place in the space, then I don't have a flat space. When we were working in a flat plane, the thing that really made everything nice was the Euclidean parallel postulate. This is what lets me think about whether a vector at a distant point is the same as the vector at some other point. If I draw this vector in a flat space, even if I'm using curved coordinates, the geometry is Euclidean. There's a straight line direction along which that vector points. Pick another point. There's exactly one straight line that passes through this point that is parallel to the line along which this vector points. Travel outwards in the same direction, the same distance as you did on the first vector, and you've got a clone of the vector. In Calculus 3, we call such things equivalent. This is what lets me pretend that I can move vectors around any way I like and it doesn't matter. What if I'm on a curved surface? What if I calculate some of those R, alpha, beta, gamma, delta numbers and some of them come up different from zero? I could be on some sort of curved surface like this. It might have a big high spot. It might have a low spot. It could have all sorts of interesting behavior. I take a point P and a point Q and ask you to tell me the vector from P to Q. In this new context, that doesn't even make any sense. What am I supposed to do? go up to the top of the high spot, and then go down to Q so that my arrow would look like that. Or maybe I'm supposed to try to stay as close down to the bottom as I can. I'll start here at P and travel along the bottom of the thing until I get to Q so that my vector would look like that. Or maybe I should start at P, go kind of halfway up and have some oscillatory motion, and then end up at Q. So my vector would look like that. This picture is a lot more agreeable than this picture is. As it stands right now, in a curved space or curved space-time, we don't have any clear idea of what a vector is anymore. Also, since we used vectors to define one-forms, we have no idea what a one-form in this kind of space is either. But it was that vector is an arrow thing that let us develop all of our major tricks. I'm just letting that sink in for a minute. All of the work that we have done is pointless. It has no utility to it whatsoever. That's kind of distressing. It's going to turn out, though, if we become a little bit more sophisticated in our thinking, we can fix this. There's going to be certain things that we can't fix. If I give you a vector located at a point, and then I give you a vector located at a very distant point, the question, are these two vectors equivalent to each other, doesn't even make any sense. Unless I tell you more, but we'll talk about that another time. All of the formulas that we've developed, how do components of vectors transform? How do basis vectors transform? Components of one forms, basis one forms, raise and lower indexes to turn one forms into vectors and vectors into one forms. The whole business about how to calculate Laplacians and multiple integration, the geodesic equation, all of this stuff will turn out to work exactly the way it worked in flat space, except we have to be a little bit careful about the context. More to come. In the meantime, I hope everyone's having a good day. I'll talk to you again soon.